Welcome back to our channel, and today we are going to plot the bending moment diagram as well as the shear force diagram for this beam that is fixed at the end A, supported at B, and on its end C it is also supported. And we are going to begin with calculating the maximum bending moment on the span A to B, and the maximum bending moment as well on the span B and C. And we are going to begin with the span AB. Therefore, we go to the span A to B. And for the span AB, the maximum bending moment will be given by W1 L1 squared divided by 8, which in this case we are going to have W1 is 6 kilonewtons per meter multiplied by the span over which it is distributed, that is 4 meters. We square it and then we divide that by 8, and when we do so we are going to get a maximum bending moment of 12 kilonewtons meter. So that is the maximum bending moment between the span A, B. Likewise, the maximum bending moment between the span B, C will be given as follows. Therefore, we go to the span B to C, and the maximum bending moment will be given by W2 L2 squared divided by 8. That's the formula of calculating the bending moment when we are dealing with a uniformly distributed load. So in this case, this is going to be 6 multiplied by 4 squared. The span BC is also 4 as well, and then we divide this by 8. And when we do so, we are going to have a maximum bending moment of 12 kilonewtons meter. Then the next thing we are going to do, we are going to plot the bending moment diagrams for the both spans, and we are going to have a smooth curve approximating that point to be 12 units from the line of origin. Likewise, on the span BC, we are also going to have a very smooth curve with a maximum bending moment of 12 kilonewton meter. On this side again, 12 kilonewton meter. Good. Then from there, we are going to calculate the area of each of these bending moment diagrams, as well as the distance of their centers of gravities from A and C respectively. Therefore, we are going to extend an imaginary zero span, like this, and we are going to call this a support, or this end we are going to call it A naught, and the distance from A naught to A is going to be L naught. So we have L naught there. So we are going to begin with the span. So we go to the span A naught A. So for the span A naught all the way to A, which is an extended imaginary span, the area, that is A naught, is going to be 0, and bar X is also going to be 0. And from there we go to the span A to B. The span AB, we have a smooth curve, and we are going to begin with calculating its area, and the area of that smooth curve will be given by this formula: 2/3 multiplied by its base, which is AB, that is 4 meters, multiplied by its perpendicular height, which is 12 units, and that's going to give us an area of 32 square meters. Therefore, A1 is equals 32 square meters. Then bar x1, and in this case bar x1 will be the distance from the center of gravity of this bending moment diagram all the way to the end A. So this is bar x1, and bar x1 will be given by half the span A to B. So that is going to be half of 4 meters, which is 2 meters. So that is the value of bar x1, 2 meters. Then we are remaining with the span BC. So for the span B to C, A2, this is going to be A1 and this one is going to be A2. Area of the second smooth curve or the second bending moment diagram is going to be 2/3 multiplied by its base, that is the span B to C, which is 4 meters, multiplied by its perpendicular height, which is 12 units, and that's going to give us an area of 32 square meters. So that's the area A2. Then we need bar x2, and in this case bar x2 is the distance from the center of gravity of this second bending moment diagram all the way to the end C. So that's what we have as bar x2, and bar x2 as well will be given by half the span B to C. So this is a half of B to C, which is 4 meters, and that is going to give us bar x2 to be 2 meters. The next thing we are going to do is we are going to apply the 3 moment theorem, and in this case we are going to begin with the spans A0A and AB, and our 3 moment equation is going to be as follows. So we are going to have m0 L0, that is m0 multiplied by L0 plus 2ma into L0 plus L1. So that is going to be like 2ma multiplied by L0 plus L1 on the other hand, plus mb multiplied by L1 all the way to A. So we have mb multiplied by L1. This is going to be equal to 6a0 bar x0 divided this by L0 plus 6a1 bar x1 divided by L1. So that's going to be our 3 moment equation for the spans A0A and AB. Now m0 L0, that is 0 plus 2ma into L0 is 0 plus L1, that is 4 meters, plus MB L1 is 4 meters, therefore we are going to have 4MB. This is going to be equal to this part, going to have 0 plus 6 multiplied by A1, which is 32 square meters, multiplied by bar x1, which is 2 meters, divided by L1, which is 4 meters. We are going to have this 2 times 4, that is 8, so we got 8ma plus 4mb being equal to, that is 0, 6 times 32 times 2 divided by 4, that's going to be 96, so that's going to be equal to 96. Then we are going to divide through by 4, and when we do so, we are going to have 8 divided by 4, that is 2ma plus mb is equal to 24. This is going to be our equation 1. So we got our equation 1 that way. Then from there, we are going to go to the spans AB and BC. AB and BC. So for the spans AB as well as BC, we are going to have the following equation: MAL plus 2mb into L1 plus L2 plus MCL2 will be equal to 6A1 bar X1 divided by L1 plus 6A2 bar X2 divide this by L2. Now, MC, since the NC is, we can't say that it is simply supported, the bending moment at C is going to be 0, and therefore MC is equal to 0. So we now have the bending moment of one of the supports. So we are going to remain with MA L1. L1 is 4 meters, therefore that's going to be 4MA plus 2MB into bracket. L1 is 4, L2 is 4 as well. That part is 0, is equal to 6 multiplied by 32 times by x1, which is 2, divide this by 4, plus 6 times A2, 32 square meters, by x2, 2 meters, and then we divide that by 4 as well. And we are going to have 4MA plus 4 plus 4, that is 8. 8 times 2, that is 16. So 16MB being equal to, that part is going to give us 96 plus 96. And we are going to have 4MA plus 16MB being equal to 96 plus 96, that is 192. Then we are going to divide the root by 4, and when we do that, we are going to have MA plus 4MB being equal to 192 divided by 4, that is 48. And this is now going to be our equation 2, that is our second equation. So equation 2. Then from there, we are going to solve equation 1 and equation 2 simultaneously. Equation 1 is 2MA plus MB, which is equal to 24. Equation 2 is MA plus 4MB is equal to 48. So this is what we are going to do. We are going to multiply the first equation with 1 or by 1. The second equation we multiply by 2. So multiply that by 1, multiply that by 2. And when we do that, we are going to have the following. And this is going to be 2MA, that is 2 times 1, plus MB is equal to 24. The second equation, MA times 2, that is 2MA plus 2 times 4, that is 8MB is equal to 48 times 2, that is 96. Then we are going to subtract equation 2 from equation 1. And that's going to give us, this part is going to be 0, 2MA minus 2MA, that is 0. MB minus 8MB, that is negative 7MB is equal to 24 minus 96. 24 minus 96, that is negative 72. So that's going to be equal to negative 72. Then from there we divide both sides by negative 7. Negative 7. And that is going to give us the bending moment at B being equal to 10.286. So we got 10.286 kilonewtons meter. So, ladies and gentlemen, that is the value of the bending moment MB. Good. From there, we are now going to calculate the bending moment at A. And in this case, we are going to use this first equation, which states that 2MA plus MB is equals to 24. So we are going to substitute the value of MB at this point. And this is going to give us the following. 2MA plus MB, which is 10.286. 10.286 is equal to 24. Is equals to 24. We take 10.286 the other side of the equal sign. That's going to be 2MA is equal to 24 minus 10.286. We are going to have this. 2MA is equals 24 minus 10.286. That is 13.714. 13.714. We are going to divide both sides by 2. And when we do that, we are going to get the value of MA being equal to 6.86. 6.86 kilonewtons meter. Therefore, ladies and gentlemen, that is now the value of the bending moment at the fixed end A. The fixed end A. Very good. So we now have the 3 bending moments that we need. And after that, we are going to plot the bending moment diagrams due to the support moments. Starting with the bending moment at A, which is 6.86. Maybe somewhere here. So we have 6.86 kilonewtons meter. Then from there we got the bending moment at B, 10.286, just a few units below 12. So this is 10.286 kilonewtons meter. And bending moment at C is 0. So what we are going to do, we are going to join this one to the line of origin. Then from there we join 6.86 to the 10.286 kilonewton meter, the straight line, and then we drop this 10.286 all the way to the bending moment at C, which is 0. And ladies and gentlemen, this is going to be positive bending moment. This one is going to be negative bending moment. This one is a positive bending moment. And here we are supposed to have just a small gap here, which is a negative bending moment. Then after that, we are going to shade off the outline of our bending moment diagram for it to be clear and visible. And just to remind you, if you are here and you are ready to subscribe, please consider doing so. So that's how we plot the bending moment diagram for this or for such a beam. Very good. So after plotting the bending moment diagram, the next thing we are going to do, we are going to calculate the reactions, that is reaction at A, reaction at B, as well as reaction at C. And those reactions, when we get them, we are going to use them to calculate the shear forces, which we are going to use to plot the shear force diagram. And in this case, we are going to begin with the span B to C, and we are going to take moments about B from the end C. Therefore, for the span BC, taking moments about B, we are going to get the following. And ladies and gentlemen, you should remember this, that the sum of clockwise moments must be equal to the sum of anti-clockwise moments. And therefore, we are going to have the following anti-clockwise moments. RC times 4, that is an anti-clockwise moment. Therefore, we got RC multiplied by 4 plus another anti-clockwise moments, that is the bending moment at the support B, which is 10.286, which will be equal to, between the span C and B, we have a UDL of 6 kilonewtons per meter. We are going to convert it to point load by multiplying it by the span over which it is distributed, which is going to act at the mid span of B and C. Therefore, the whole of that span divided by 2. and this is going to give us RC times 4, which will be equal to 6 times 4 times 4 divided by 2, that is 48. Then we take 10.286 the other side of the equal sign, that's going to be minus 10.286, and this is going to give us RC multiplied by 4 being equal to 37.714. That's 7.714. And then we are going to divide both sides by 4, and when we do so, we are going to get a reaction at C being 9.43 kilonewtons, and therefore the reaction at C is 9.43 kilonewtons. Then from there we go to the span AB. Therefore, for the span A to B, taking moments about B as well. So this is what we are going to have: RA multiplied by the distance from A to B, which is 4 meters. That is a clockwise moment. Therefore, RA times 4. We add another clockwise moment at B, which is 10.286. Therefore, plus 10.286 will be equal to the bending moment at A, which is 6.86. So we add bending moment at A, 6.86, which in this case is an anti-clockwise moment. That moment there is an anti-clockwise moment. It will be added to this anti-clockwise moment. Between the span A and B, we have a UDL of 6 kilonewtons per meter. Convert it to point rod. We multiply it by the span over which it is distributed, which will act at the midspan of A and B, that is 4 divided by 2. And this is going to be RA times 4 plus 10.286 being equal to 6.86 plus 48. That is going to be 54.86. So is equals 54.86. This is going to be RA times 4, which is going to be equal to 54.86. We subtract 10.286. So minus 10.286. And when we do that, that is going to give us 44.574. 44.574. Then to get the value of the reaction at A, we are going to divide both sides by 4. And when we do so, we are going to get a reaction at A being equal to 11.14 kilonewtons. Very good. Then we are remaining with the reaction at B, and in this case we are going to say this: the sum of all the upward acting forces, that is RA plus RB plus RC, must be equal to the sum of all the downward acting forces. And in this case, the whole span is loaded with a UDL of 6 kilonewtons per meter, and the whole span is equivalent to 8 meters, and therefore the point rod is going to be UDL multiplied by the span over which is distributed. Reaction at A is 11.14. Reaction at B, we are yet to know its value. Reaction at C, 9.43 kilonewtons, is equal to 6 times 8, that is 48. This is going to be RB, which is going to be 48. 11.14 plus 9.43, that is 20.57. When we bring it this side of the equal sign, it's going to be minus, therefore we have minus 20.57. And ladies and gentlemen, this is going to give us a reaction of 27.43. 27.43. 9.43 kilonewtons. Therefore, that is the reaction at the support B. So we got all the three reactions that we need, and we are going to write them here. RA 11.14. So we write there 11.14 kilonewtons. Reaction at B 27.43. So we got 27.43 kilonewtons. Reaction at C 9.43 kilonewtons. This is on kilonewtons. Very good. Now, after getting the value of the three reactions that we need, the next thing will be shear force calculations. And in this case, we are going to begin with the end C. So we have the shear force at C, which will be equivalent to the reaction at C. That is 9.43 kilonewtons. 9.43 kilonewtons. Then we go to shear force between C and B. So you go to shear force between C and B, which is going to change uniformly from 9.43 kilonewtons, 9.43 kilonewtons, minus the load between C and B, that is a UDL of 6 kilonewtons per meter, multiplied by its span, which is 4 meters, and that's going to give us 24. 9.43 minus 24, that is negative 14.57 kilonewtons. 57 kilonewtons. And from there we go to the shear force at B. So the shear force at B is going to be this shear force between C and B of negative 14.57. We add the reaction at B, which is 27.43. So we add 27.43. And when we do so, we are going to have 12.86 kilonewtons. 12.86 kilonewtons. Then from there, we go to shear force between B and A. Therefore, shear force between B and A, it is going to change uniformly from 12.86 kilonewtons, 12.86 kilonewtons, all the way to 12.86 minus the UDL between B and A, which is 6, convert it to point rod, multiply it by 4, that happens to be 24. Therefore, 12.86 minus 24, and that is going to be negative 11.14. Negative 11.14 kilonewtons. Then finally, we determine the shear force at A, and the shear force at the end A, or the fixed end A, is going to be equal to the shear force between B and A. Therefore, that is negative 11.14 kilonewtons. And therefore, ladies and gentlemen, we now have all the shear forces. This is how our diagram is going to look like. We are going to begin with the end, with the support C. And remember, the positive shear forces will appear above this horizontal line, and the negative shear forces will appear below this horizontal line. The shear force at C is 9.43, so let us have it at that point. So that is 9.43 kilonewtons. Shear force between C and B will change uniformly from 9.43 to negative 14.57. So negative 14.57, let it be there. So we got 14.57 kilonewtons. So we are going to join 9.43 kilonewtons to this negative 14.57 kilonewtons. Then we join it to the horizontal line. I want this be as straight as possible. Correct. Then from there we have the shear force at B, which is 12.86 above 9. So here we have 12.86 kilonewtons. We are going to join that to the horizontal line. Then the shear force between B and A is going to change uniformly from 12.86 to negative 11.14. So negative 11.14 above 14. So this is 11.14 kilonewtons. And we will see that the shear force at between B and A is equivalent to the reaction at A. So the uniform change, we are going to join this 12.86 to this 11.14 kilonewtons. Hope that is going to be straight. A good try. Shear force at A, negative 11.14. So ladies and gentlemen, that is our shear force diagram. And what we are going to do, this shear force is going to be negative. This one is negative. This one is positive. This one is positive. And then finally, we are going to shade off the outline of our bending of our shear force diagram. We are going to shade off the outline of our shear force diagram so that it appears more clear and visible. Keep on subscribing, like, comment, and share. So thank you very much, ladies and gentlemen, and thank you for watching our video. And please, if you are here and you are ready to subscribe, please consider subscribing, and don't forget to hit the notification bell so that anytime we record and upload new content, you'll be the very first person to be notified. So we thank you very much. Let's meet here again in yet another episode of structural engineering.